In the previous episodes, we explored how energy moves through the climate system. Solar radiation heats the Earth's surface, but a large portion of that energy does not immediately increase temperature. Instead, it evaporates water. The energy becomes stored as latent heat and is transported through the atmosphere as water vapor. When vapor condenses, latent heat is released, helping to drive atmospheric motion and cloud formation. We saw that latent heat does not add energy to the climate system, but it changes when, where, and how solar energy is released back to space. But this raises an important question. If water is one of the main carriers of energy in the climate system, what determines how much water enters the atmosphere? Over the oceans, the answer is relatively simple. Evaporation depends mainly on temperature, wind, and humidity. Over land, however, another factor becomes extremely important: vegetation. Plants do not simply exist within the climate system. Through evapotranspiration, they actively participate in the transfer of water and energy between the land surface and the atmosphere. In 2023, Brian Huntley and his research team published a remarkable reconstruction of past vegetation patterns. Using pollen preserved in sediments and other fossil evidence, they reconstructed global biome distributions over the past 800,000 years. This data set shows how major vegetation types shifted during glacial-interglacial cycles, revealing large changes in the distribution of forests, grasslands, tundra, and deserts across different latitudes. When the total global area of forests is compared with temperature reconstructions derived from ice cores and other climate proxies, a striking pattern appears. Forest cover and global temperature follow very similar long-term trends during glacial cycles. For much of the record, they appear to move almost together. Because the dataset has a temporal resolution of about 4,000 years, it is often difficult to determine which variable begins changing first. However, in cases where the turning points can be distinguished more clearly, vegetation changes frequently appear to begin slightly earlier than the corresponding temperature shifts. This pattern may also be visible around the last glacial maximum, about 22,000 years ago. On the graph, both forest coverage and temperature begin to change around 20,000 years ago. Although the Huntley dataset generally has a temporal resolution of 4,000 years, up to about 24,000 years ago, it contains data at 2,000-year intervals. This allows the period around the last glacial maximum to be examined at somewhat higher resolution. The same pattern also appears in this graph. It suggests that forest coverage had already begun to change near the last glacial maximum, while temperature began its sustained increase only several thousand years later, around 18,000 years ago. At present, this observation alone is not sufficient to establish a causal relationship. Both vegetation and temperature respond to multiple processes within the Earth system. Nevertheless, considering the buffering role of oceans and polar ice discussed in Part 3, which can delay the full temperature response to changes in energy balance, the possibility arises that vegetation may play a more active role in climate dynamics than is often assumed. Several characteristics of forests help explain their high evapotranspiration capacity. Tree roots can access water much deeper in the soil than smaller plants, allowing evaporation to continue even when the upper soil layers are dry. Forests also have large leaf areas, which increase the surface available for transpiration. Agricultural ecosystems can exhibit similar behavior. Crops are typically planted densely to maximize productivity, and irrigation often provides additional water when rainfall is insufficient. As a result, agricultural landscapes can also sustain strong evapotranspiration. Vegetation change is not limited to the distant past. It has also been occurring rapidly in the modern era. One widely used reconstruction of historical land use is the Land Use Harmonization dataset. These data describe how forests, croplands, and pastures have changed over the past several centuries. Around 1700, agricultural land started expanding rapidly across many regions of the world. Forest area declined in some regions, while other regions experienced regrowth. In terms of water and energy exchange with the atmosphere, agricultural ecosystems often share several characteristics with natural vegetation. Many agricultural landscapes, particularly irrigated ones, can sustain substantial evapotranspiration like forests. When forests and agricultural lands are considered together, the total area of these vegetation types increases significantly in and after the 18th century. Global temperature records show a pronounced warming trend beginning around 1900, roughly 200 years later. This comparison alone does not demonstrate causality. Many factors influence the climate system. However, it highlights an interesting observation. Changes in vegetation distribution have occurred both during glacial cycles and during the modern period, and these changes often appear to precede temperature shifts. This pattern certainly provides grounds to investigate the energetic role of vegetation more closely. If you like the video so far, don't forget to subscribe to the channel. Remember, this fifth part is only about halfway through the series, and the really interesting part is just about to come. We plan to release new episodes weekly, and subscribing to the channel ensures you don't miss any of them. Across the world, hundreds of research towers continuously measure how ecosystems interact with the atmosphere. These measurements form the global FluxNet network. Flux towers measure the exchange of carbon dioxide, water vapor, and energy between the land surface and the atmosphere using a technique known as eddy covariance. Among the measured quantities are two key components of the surface energy balance. The first is sensible heat, which directly increases air temperature. The second is latent heat, which represents the energy used to evaporate water. For illustration, several towers representing different vegetation types around the world can be examined. Measurements from many ecosystems show that vegetation can transfer a substantial amount of energy into the atmosphere through evapotranspiration. Data from flux towers illustrate how strongly this process depends on vegetation type. Evapotranspiration is typically very low in deserts, where water availability is extremely limited. In contrast, forests and other ecosystems often show much higher latent heat fluxes. Using values derived from FluxNet observations, eddy covariance studies, and ecological literature, representative latent heat flux values can be assigned to the biome categories used in the Huntley Paleovegetation reconstruction. Tropical evergreen forests often exhibit latent heat fluxes exceeding 100 watts per square meter. Temperate forests generally show somewhat lower but still substantial values. Grasslands and savannas typically fall within intermediate ranges. Tundra ecosystems exhibit lower fluxes, reflecting colder climates and shorter growing seasons. Deserts and sparsely vegetated regions generally transfer much less energy through latent heat due to the limited availability of water. The first column of the table shows the biome code used by Huntley for the 800,000-year time series, and the last column shows the latent heat value assigned to that biome when calculating the effect of latent heat on global temperature. These values are not fixed constants, but mean values calculated from data measured over time. The actual latent heat flux varies between day and night, with climate, season, and local conditions. These averages, however, provide a useful first-order estimate of how different ecosystems exchange energy with the atmosphere. If each biome type is associated with a characteristic latent heat flux, then large-scale changes in global vegetation may influence the total amount of energy transferred into the atmosphere through evaporation. Using the reconstructed biome distributions from paleovegetation studies and representative latent heat values for each biome, it is possible to estimate how global latent heat flux may have varied during the past 800,000 years. In this approach, the global latent heat flux at each point in time is estimated by combining the area of each biome with its characteristic flux value. This produces a first-order reconstruction of how vegetation changes may have influenced the latent heat component of the climate system during glacial cycles. The resulting curve suggests that global latent heat transfer varies as vegetation expands and contracts across the planet. Periods with more extensive forests and productive ecosystems tend to correspond with higher latent heat transfer to the atmosphere. Periods dominated by tundra, grasslands, and deserts tend to correspond with lower latent heat flux. When compared with temperature reconstructions, the changes in latent heat show a clear relationship with temperature variability. The magnitude of the latent heat variations appears smaller than the full amplitude of glacial-interglacial temperature changes, but it still represents a substantial portion of the total variability. This suggests that latent heat alone cannot explain the entire temperature signal. However, the analysis highlights an important point. Vegetation is not only a passive element responding to climate. It also modifies how incoming solar energy is partitioned between heating the surface and evaporating water. Even relatively modest shifts in this energy partitioning can influence atmospheric circulation, humidity, and cloud formation. And latent heat is only one pathway through which vegetation interacts with the climate system. Vegetation can also influence how energy leaves the Earth in the form of radiation. In the next episode, we will explore another mechanism through which ecosystems may influence climate, their potential impact on the outgoing long-wave radiation of the planet. In the next part, we will further explore the role of vegetation in climate change within the boundaries of widely accepted science. In particular, we will see how it may regulate the amount of energy leaving Earth through outgoing long-wave radiation. If you liked this part, don't forget to share the video so others may also enjoy it. Also remember to like the video and subscribe to the channel so you don't miss the next part and other exciting videos released in the future.